Welcome aboard the 192.168.0.0/16 Express, your non-stop ride into the world of subnetting. Today, we're going to tackle a fun challenge about overcrowded carriages, underutilized space, and last-minute problem solving. It's going to be a wild ride, so buckle up. Let's break this down. Imagine the train is your network, and each carriage represents a subnet. Our train, the 192.168.0.0/16 Express, has 4 carriages, or subnets, each set up as a /24 subnet with room for 254 passengers. Think of each passenger as a computer or a network device with its own IP address. Here's the problem. Carriage 4, reserved for Manchester, has only 96 passengers, far below its capacity. Sounds fine, right? Well, not so fast. Meanwhile, on the next platform, a train bound for Glasgow had a serious engine failure. With no time to repair it, the conductors scrambled to find a solution. Although only 112 passengers need to get to Glasgow, their journey is urgent. And guess what? The 192.168.0.0/16 Express has just enough room, if we're clever about it. This is where subnetting comes to the rescue. Instead of wasting space, we divide carriage 4 into 2 smaller subnets, each tailored to its specific group. Glasgow, 112 passengers. Manchester, 96 passengers. We allocate 192.168.5.0/25 for Glasgow. That's 128 IPs for their 112 passengers. 192.168.5.128/25 for Manchester. That gives us 128 IPs, perfect for their 96 passengers. This way, everyone gets a seat and no one's left stranded. Let's take a look at our updated train map. Carriage 1, Oxford. Carriage 2, Birmingham. Carriage 3, Liverpool. Carriage 4, Manchester. Now, we split carriage 4 into 2 subnets, Glasgow and Manchester. The train master didn't just solve the problem, he optimized the train for maximum efficiency. Subnetting isn't just about solving problems like this, it's a game changer for networks, and here's why. Efficiency. We avoid wasting space on underutilized resources. Isolation. Manchester and Glasgow passengers or devices don't interfere with each other. Each is a separate subnetwork. And security. By keeping traffic separate, we reduce the risk of mixing sensitive workloads. And in this case, we kept the whole train moving without leaving anyone behind. And that's how subnetting saves the day, train style. Now, I know what you're thinking. Okay, subnetting lets us split larger networks into smaller ones. But how does it actually work? How does changing the /24 to a /25 at the end of an IP block actually splits it into subnets? And how does it ensure that traffic or passengers heading to Manchester stay separate from those bound for Glasgow? To dive deeper into the architecture of IP addressing and learn step by step how subnetting works and how it keeps your network isolated, keep watching this video and we'll proceed into the technical details. Hit the like button, subscribe for more tech made simple, and get started with the magic of subnetting. So let's talk about IP addresses and subnetting. Now, as I mentioned previously, an IPv4 address is a 32-bit address scheme. It's 32 bits of ones and zeros. You remember, right? Computers talk only in binary. And so these 32 bits of ones and zeros are binary representation of an IP address. To you and me, an IP address may look like 192.168.1.7 or whatever else it might be. But to the computer, it's 32 bits of ones and zeros that represents that particular IP address. Now I want to show you something. Take a look at this network. I've got 2 devices here. I've got 192.168.7/24 and then 192.168.110/24. You've seen this /24/16/8 in your research into networks previously, I'm sure. What do they actually mean? Let's take a look at another set of IP addresses. This is another set of IP address, 192.168.2.7/24, 192.168.2.10/24. My question to you is, are these 4 devices in the same network? The answer is no. The top one, 192.168.1.7 and 192.168.1.10, with the /24 represents one network. However, 192.168.2.7/24 and 192.168.2.10/24 is yet another network. These 2 networks are not the same. They are separate. They're isolated from each other. Sure, you can send traffic between these networks by adding something called a router in between and routing traffic across, but by default, these networks are 2 separate networks, and that's because of subnetting, and that's because of the /24. So what does this all mean? Well, let's start from first principles. A device requires an IP address to communicate over a network. We know that already. An IPv4 address actually helps you identify the network it belongs to, as well as the address of a particular device, this particular computer here, for example. So your IP address actually consists of 2 parts. It consists of a network portion that identifies the network to which the device belongs to. In this case, we've got 2 networks, network 1 and network 2, and a host portion that actually identifies the specific device, or the host machine, if you will, within that network. 192.168.1.7/24 and 192.168.1.10/24 is one network. The .7 and the .10 are for 2 separate devices. Let's take a look at the example in a bit more detail. Take the IP address 192.168.1.10/24. What does that mean? The /24 indicates that the first 24 bits represent the network portion of your IP address. Remember, we've got 32 bits in your binary system. We're taking 24 bits off that 32-bit system to represent the network portion, which means that the first 3 octets actually represents the network. So the 192.168.1 for this device and the 192.168.1 for this device fall within the same network. Likewise, 192.168.1 is a different network to 192.168.2 because of the /24, because we've taken the first 3 octets, if you will, to represent the network. And so these 3 decimal numbers, these 3 octets, represents the network portion of your IP address. The last octet is what's representing the actual host IP address of the machine. Thus, the remaining bits represent the host portion. So a device with an IP address of 192.168.1.5/24 is in the same network as a device with 192.168.1.7/24. However, if this IP address were a 192.168.2.7, that would be a completely different network from this IP address because of the /24, because we're taking 24 bits to represent the network, the first 3 octets. Now I know you really want to understand exactly how this works. So let's dive a little bit deeper. So just to reiterate, what we want to try and understand is, how is it that these 2 networks are separate? How is it that the device with 192.168.1.7/24 on a different network when compared to 192.168.2.7/24? Now I've explained that it is because of the /24, because 24 bits effectively takes the first 3 octets of your IP address and defines a network component to it, a network portion of it. But the question still arises, how does it actually work? How is it that by using a /24, the 192.168.1 something is on a different network from 192.168.2 something, and there's yet another network that starts with 192.168.3 something? How are these 3 networks separate? How are they isolated from each other? Because that's what the /24 does. Now the answer to that is all to do with subnetting. But before diving into subnetting, let's take a step back and actually try to understand how is it that a typical decimal IPv4 address, or 192.168.2.7 in this case, can be converted into its binary format, because therein lies the entire trick of the game. Okay, so let's move on and talk a little bit more about converting decimal IP addresses to their binary equivalent. So next, let's talk about how we can convert decimal to binary for IPv4 addresses. Here is a typical IP address 192.168.1.5. Now in decimal, we already know that this can range between 0 to 255. Each octet in this IP address can range from 0 to 255 as a base 10 value or a decimal value. Convert each of those octets into binary, the maximum you can get is 8 bits of ones or zeros. So ranging from 8 zeros all the way up to 8 ones. Why is the question? Well, that's because binary is a base 2 numerical system where each digit or each bit in the binary number represents a power of 2, starting from 2 to the power of 0 for the rightmost digit and increasing as you move left till you get to 2 to the power of 7, because that's the maximum. For an 8-bit binary number, which are common in computer system, the rightmost bit represents 2 to the power of 0. What does that mean? Well, that means 1. 2 to the power of 0 is 1. Similarly, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, 16, 32, 64, 128. These powers of 2 combine to represent any decimal number. Why are we using powers of 2? Why are we doing 2 to the power of 0 all the way to 2 to the power of 7? That's because it identifies our range of values. Using 8 bits, it allows us to represent the numbers from 0 to 255. Because if in your binary representation of that particular octet, you got all ones, okay, so if each of these x's were a 1 instead of a 0, then the value of 255 would be achieved because you're basically converting each of these into their decimal representation, and 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 is equal to 255. So the range comes from summing up all of the powers of 2. Similarly, you've got the same representation for each of the other octets. Okay, so now that we understand how decimals are converted into binary, let's take a look at how a particular octet in that IP address, what is its representation in binary? So the conversion from decimal to binary is based on the fact that you're going to use specific placeholders in binary to get to that 192. Okay, so in the case of 192, the quickest way or the simplistic way of getting to 192 is if we converted this x to 1 and this x to 1. Why? Because if we convert this x to 1, that will give us 128. And if we convert this x to 1, that will give us 64. Now 128 plus 64 is 192. There's our 192. In the same way, to get my 168 in this IP address for the second octet, all I need to do is convert this x to 1, which will give me my 128, this x to 1, which will give me 32, and this x to 1, which will give me 8. And 128 plus 32 plus 8 is 168. In the case of the third octet, well, that's simple. 2 to the power of 0 is 1. We just need 1 anyway, so we'll just convert this x to 1. And finally, for 5, if you take 2 to the power of 2 is 4. 5 minus 4 is 1, so I just need 1. So 2 to the power of 0 is my 1. So 4 plus 1 is 5. So I just need to convert this x to 1 and this x to 1 and the others to 0. And so ultimately, when it comes to the actual conversion to binary, because I'm converting this x to 1, I got my 1. And the second x to 1, I got my 1. But the others are going to be represented by 0 because I do not need them. They're zeros. They're turned off. Okay. So my binary representation of 192 is 11000000. And you do the same for each of the other octets. So the 168 is 10101000 because we are only turning these x's to ones and the others to 0. And our third octet, we only need to convert this x to 1. And in the case of our final and fourth octet, we only need to convert this x and this x to ones. And so our 192.168.1.5 decimal IP address is the same as 100000000, 101010000, 000000001, and 000000101. in binary. And that's how you convert decimal to binary. Okay, that's fantastic. We still haven't answered the question, which is, how is it that this particular IP address 192.168.1.7/24 is on a different network from 192.168.2.7/24? And we'll do that very shortly. But for that, join me in part 2 of this video. Hello and welcome back. This is part 2 of our IP addressing and subnetting section of this video. In this video, we're going to deep dive further into how subnetting can be used to build smaller networks in the cloud. So you have a larger network where you have various services that you want to run, but you want to create smaller networks within that larger network to separate out and isolate your services. And that's where the power of subnetting comes into play. So in this video, we're going to deep dive further by looking how subnetting works. So recall from our last video, we spoke about these two different networks. We said that 192.168.1.7/24 was on a completely different network when compared to 192.168.2.7/24. And I mentioned that that was because of the /24. This /24 is what's known as a classless Internet Domain Routing number. Okay. This is essentially a number that defines exactly the network of your IP address range, okay, or your IP address. This /24 essentially means that you're taking 24 bits from the 32-bit addressing scheme that is part of your IP address. 24 bits of that are going to be used to represent the network where that device sits in. Essentially, it's taking the first 3 octets because 24 bits will occupy the first 3 octets of your IP address range. Therefore, the .1 is on a completely different network from the .2. Now, this number can change based on how large or how small you want your networks to be and how many networks you want in your more larger network. So do you want 1 network or do you want 30 networks? You can change this number, and this CIDR representation will define exactly the subnet mask that will allow you to define exactly how large or small the network is and how many networks you can have, how many smaller networks you can have in a larger network. So you can have a /20, or you can have a /16, or you can have a /28. The point is, it's this number that allows you to define the network of your IP ranges. Now, this CIDR notation, this /24, is just another way of representing subnet masks. In modern day networking, we use CIDRs rather than standard subnet masks because it's a lot more flexible. We'll come on to that a little later. But to discuss this further, let's understand exactly how subnet masks work. So we'll start off by explaining the fact that a subnet mask, like an IP address, is a 32-bit number that separates the IP address into a network portion and a host portion, defining which part identifies the network and which part identifies devices within that network. It does this by masking the IP address with a bitwise operation. Okay, so the subnet mask is used to mask the IP address with a bitwise operation to work out the network portion, and therefore whatever's remaining is the host portion. It's a 32-bit binary number composed of 1s and 0s, like an IP address, but the 1s and 0s mean different things. The 1s represent the network portion, and the 0s represent the host portion. So whereas with an IP address, the 1s and 0s represented, for example, 192.168.1.7, with the case of a subnet mask, the 1s are used to represent the network portion, and the 0s are used to represent the host portion. And therefore, the decimal representation of a subnet mask can be anything from 255.0.0.0 all the way up to 255.255.255.255. Okay? When the subnet mask is applied to an IP address using this bitwise AND operation, it reveals the network address by retaining the network portion, identifying all the 1s, and discarding all the host portion, which is defined by the 0s. So another way of describing this is that this /24 is the same as 255.255.255.0. Okay, and that is because 24 simply represents 24 bits. We're taking 24 bits of the IP range to be representing the network. Therefore, they're all going to be converted to 1s. Therefore, 255.255.255. And the last 8 bits are going to represent the host. So we only got 8 bits left within which you can have IP addresses for your devices. The same thing with the other network as well. The 24 means that we're taking 24 bits of the IP address range to represent the network. They're converted to 255.255.255.0, and the 0 at the end is left for the host portion of your IP range. That's where you're going to get your IP addresses for your devices from. Now, obviously, the next question is, can we see this bitwise operation? Can we see how these two networks are actually separate from each other? And we'll come on to that very shortly. Before we do, I just want to talk to you a little bit about the default subnet classes within IP addressing. So let's start by taking a look at your default subnet mask. So you've got a class A subnet mask, which is 255.0.0.0. Here, what we're doing is we're taking the first octet, or 8 bits, to represent the network, and the remaining 24 bits are used to represent the host machines. Okay, so what this means is that you can have 2 to the power of 8 set of networks, okay, but each network can have up to 16 million odd IP addresses, because your host bits, you've got 24 bits available to use. 2 to the power of 24 is 16,007,777,216. And so you can have that many IP addresses per network. So this is where you have really large networks, okay, that you can have in your organization. The next one is a class B. This is another default subnet mask. Now, a class B uses 16 bits for your network, so the first 2 octets, and 16 bits for the host. And in this case, you have 2 to the power of 16, which gives you 65,000 odd IP addresses. What this basically means, therefore, is that you can have far more networks, 16 bits, 2 to the power of 16, that many set of networks, but each network can have a maximum of 65,536 IP addresses. Okay. Then we have a class C. A class C is 255.255.255.0. Here we are using 24 bits of your 32-bit addressing scheme to represent the networks, and only 8 bits are left to represent the host. So here you can have vast amounts of networks, millions of networks, but each network can only have up to 256 available IP addresses. Your decision as a solutions architect is how many networks do you need in your organization, and how many IP addresses do you need within each network. So let's talk about why subnetting is really important beyond the standard 3 classes that we are aware of. So you know that we have 3 default subnet classes. You've got the class A subnet class, the 255.0.0.0, which gives you 16 million odd IP addresses per network. You got class B, which is 255.255.0.0, which is 65,000 plus IP addresses per network. And then you got class C, which gives you 256 IP addresses per network. And this generally is enough for most organizations, but often you might need to actually build networks that need more IP addresses or less IP addresses. So you may require a network that only needs 4,000 IP addresses, not 256, that's too small, and definitely not 65,000. That's where subnetting comes in. That's where using CIDR ranges or CIDR notations come in to help you build flexible subnetworks. So let's just reiterate what subnetting is. It is a way of dividing a large network into smaller, more manageable subnetworks. This helps efficient IP address usage, so preventing waste IP addresses by allocating only the number needed for a specific subnet. Network segmentation, improving security and performance by isolating parts of the network. So your workspace area where all of the employees sit in the office should be on a separate network or subnetwork when compared to where all the servers and databases are sitting. Okay. When traffic needs to enter the server area to access the service, then it should be routed through routers. But all of the network noise that happens within the workspace area, within where all of your employees sit with all of their laptops, desktops, printers, scanners, photocopiers, all of that stuff, shouldn't be allowed to have direct access into the server network area, because that increases a lot of traffic. Okay, and it also helps you improve security and therefore performance. Simplified management, you can organize large networks into smaller logically grouped subnetworks. So you can have a 192.168.0.0 with a class B subnet mask divided into smaller networks of a class C subnet mask. So you got the 192.168.1.0 with the class C subnet mask, 192.168.2, that's a different subnetwork with the class C subnet mask, and so on. Without subnetting, you're going to end up with just one flat network. Okay, so all of your servers are going to be in the same network, the same room, if you will, as all of your workstations, mobile phones, printers, photocopiers, and all that stuff. Okay, and this has a lot of disadvantages, including excessive broadcast traffic, which is where all devices share a single broadcast domain, leading to high broadcast traffic, reducing bandwidth and degrading performance as the network grows. Poor security. Devices lack isolation, making network vulnerable to malware spread and unauthorized access to sensitive systems. Complex management. Troubleshooting can be difficult, but no logical separation of devices, and network policies, ACLs, cannot be applied effectively. Okay? So subnetting resolves these issues by improving performance, security, and manageability. So what I want to do next is I want to come back to our original question in part 1 of this video, where we showed 2 different devices, okay? 192.168.1.7/24 and 192.168.2.7/24. And I want to walk you through exactly how they are on separate networks. Let's do that next. So let us talk about how applying subnet masks can actually help you create these separate networks. One of the things we spoke about in the last video was the fact that when you apply a subnet mask and you perform something called a bitwise AND operation against your IP address range, you can derive the network that that IP range is in. Okay, so the thing you got to understand and remember here is that in binary, you can either have ones or zeros. Now, 1 is either on or true, and 0 is off or false, right? So either it is on or off, true or false, 1 or 0. And when you come to perform an AND operation, you need to understand what exactly is happening. A bitwise AND operation is basically a logical operation that's used in computing, math, and logic to combine 2 or more conditions or values. And what it does is it evaluates whether multiple conditions are simultaneously true. So if we take a look at this table, let's say you've got 2 sets of values for A and B. When you perform an AND operation between A and B, the key concept here is that a 0 and a 0 will always yield a 0. 0 and 1 will still give you 0. 1 and 0 will still give you 0. 1 and 1 is the only time you will get a 1. Okay? So this is critical when performing an AND operation. This is how subnet masks work with your IP address. An AND operation is performed. Let's take a look at our device, 192.168.1.7/24. If we were to try and convert this to its binary format, we'd go through that entire process of identifying which bits to turn on, which bits to turn it to 1, and which bits to leave at 0, turned off, to get our value of 192.168.1.7. Similarly, with our other device, 192.168.2.7/24, you do the same thing. You'd basically work out which of these bits you need to turn on, which to turn to 1, and which to turn to 0 to get your IP 192.168.2.7. Now, when you convert this decimal notation into its binary format, this is what you get after performing that operation. Similarly, this is the IP address in binary for our second device. Now, the /24, as we have been discussing in this video, is essentially a class C subnet mask. So it's a 255.255.255.0. That's because we're using 24 bits out of the 32 bits available to represent our network. The same thing with the second device. We're using 24 bits out of the 32 bits to represent our network. That's the 255.255.255. Represented as CIDR, it's a /24. So when it comes to performing that AND operation between the IP address in binary and the subnet mask in binary, this is what you get. 1 and 1 is 1, 1 and 1 is 1, 0 and 1 is 0. Okay? 1 and 0 is also 0. 1 and 0 is also 0. But all of the 1 and 1 is where you will get 1. So this represents a particular network. Similarly, the second device, when you perform a bitwise AND operation between the IP address and the subnet mask, you get a network in binary that's defined by this set of binary numbers. And if you look really closely, you will notice a key difference in the third octet. The third octet is 00000001, whereas for the second device is 00000010, a totally different pattern. And hence, the top network address is different from the bottom network address. All of the devices that fall within this address, within this network, will be easily able to talk to each other without the use of routers or route tables or any kind of firewalls in the middle. All of the devices that fall in this network will also be able to talk to each other very easily. If you need to send traffic from this device to this device, you would need to allow for some mechanism so that the devices in this network, the 192.168.1 something network, can know where the network 192.168.2 something is. And usually you'd use a router for that. Okay, and we'll talk about routers a little later. But the point is, and what I wanted to highlight with this simple exercise, is that the network that this device is in is clearly different from the network that this device is in, if only by the difference in the pattern. So hopefully this makes sense. Hopefully you can see how subnetting actually allows you to create multiple networks, okay, and separate out your workloads from each other. Right, let's move on with our topic. So next I want to talk to you about how we can use CIDR to represent your subnet masks. CIDR is just a way of representing a subnet mask, is a way of actually presenting what the subnet masks ultimately looks like. But it's a lot more flexible and a lot more versatile to use when trying to identify the network portion of your IP range versus the host portion. And it makes calculating subnetworks a lot more easier. So here we've got our two networks, 192.168.1.7.24, and then the other network, 192.168.2.7.24, two devices in two separate networks, if you will. The fact is, looking at this /24 can immediately tell you that, this is a standard class C address, okay, a class C subnet mask, 255.255.255.0. And as a result of that, the last octet has got 8 bits in it that is dedicated to the host. That's 2 to the power of 8. Therefore, each network in those networks are going to have 256 available IP addresses. Okay, so I'm instantly able to tell that by just knowing the CIDR notation. So CIDR, short for Classless Inter-Domain Routing, is a method used in networking to define IP addresses and their associated network masks more flexibly than traditional class-based addressing. The key components of CIDR are the IP address, that's the unique address assigned to a device on the network, and the subnet mask, the mask used to determine which part of the IP address identifies the network and which part identifies the host. And that is done by using the / prefix length element. So CIDR uses this compact format to express the IP addresses and their subnet masks in this CIDR notation, IP address / prefix length. The prefix length is the number of bits in the subnet mask that represent the address's network portion. So if this is a /24, that's 24 bits representing the network portion. If it was a /20, that'd be 20 bits out of the 32 bits representing the network portion. The number of remaining bits represents the host portion. So if it is a /20, then 20 bits represent the network, and 32 minus 20 is 12. 12 bits represent the host portion. Let's take a look at how CIDRs can be used to represent your standard default subnet mask. You know, the class A, class B, class C? Let's do that next. So if we were to use this CIDR notation to represent our subnet mask, let's quickly take a look at our standard default classes of subnet mask. You've got your class A, which is 255.0.0.0. That's where we're using 8 bits for the network and the remaining 24 bits for the host. To give you the CIDR notation of any IP address that falls within this class, then, you know for a fact that we're only using 8 bits, and so the CIDR notation, the prefix length, is going to be /8. Okay, so your IP address, whatever it might be, 10.1.7.17 /8 is ultimately means that it's using a class A subnet mask or a /8 CIDR notation. Similarly, when we talk about a class B network with a subnet mask of 255.255.0.0, we're using 16 bits for the network and 16 bits for the host. Therefore, the CIDR notation for any IP address in this network is going to be a /16. Okay, it's this prefix length that tells you how many bits are being used for the network. And then obviously there is the class C default subnet mask of 255.255.255.0. Here we're using 24 bits for your network, and so your CIDR notation is going to be S/24. Let's talk about creating subnetworks within a larger corporate network. So here we have a corporate office running on a 192.168.10/24. Obviously, it's not that big of a corporate office. It's only got 256 IP addresses, but that's the entire range for the corporate office. Okay, so it's using a standard class C subnet mask 255.255.255.0, which is a /24 in CIDR notation format. Okay, so a prefix of 24 bits define the subnet mask, and therefore the range of IPs that you have is 192.168.10 all the way up to 192.168.1.255. Now, if you put all of your devices and all of your servers and workstations and printers in this network, they will basically be one flat network. But what you could do is you could create subnetworks within this corporate network. We know for a fact that a /24 effectively means that we're using 24 bits of your network to represent the network. And in this case, the entire corporate office runs on that network. But within the corporate office itself, we may have subnets, subnetworks, a subnetwork for our servers and a subnetwork for our users using their workstations, maybe a separate subnetwork for our guest Wi-Fi users. And so what you want to do is you want to create these subnetworks so that they don't automatically talk to each other. They don't automatically have devices in this office staff network talking to servers directly, if you will, okay, or using broadcast traffic into the server room network. You want traffic to be routed when required using your route. So ultimately what happens there is we are extending the number of bits that we're using for our network. We already have the corporate office defined in a class C subnet mask or a /24. Within that, we are consuming an extra bit from the host portion of the block to build subnetworks. Now, in essence, what we're doing is we're borrowing a bit. We're borrowing a bit from the host portion to create our subnetworks. And in this case, we're borrowing just the one bit, the bit on the far left of this block. And so by borrowing this bit, essentially what we are doing is we are borrowing a bit from the host portion of the IP address to extend the network portion and to allow us to create those multiple smaller subnetworks within the original IP range. The way how it works is this is your main block, okay? But any bits borrowed further to create additional networks are subnetworks within that main block, okay? And so ultimately, because we're borrowing one bit, the far right bit in this block, the subnet mask will change. It wouldn't be 255.255.255 anymore. It will be whatever number of bits we borrowed. It would be the actual conversion of that bit to a 1. And so if we convert this to 1, that's 2 to the power of 7. That is 128. So the new subnet mask for our subnetworks is going to be 255.255.255.128. The original larger network for the corporate office is still 255.255.255, but the smaller networks are going to be 255.255.255.128 because we're just borrowing one bit for now. By borrowing one bit, we also end up creating two networks. Because we've only borrowed one bit, the formula for the number of subnetworks that are created is 2 to the power of n, where n represents the total number of bits borrowed from the host block. So because we're borrowing only one bit, it's going to be 2 to the power of 1, which is 2, which means we're creating two subnetworks, the office staff network and the server room network, within the corporate office network. In addition to that, the number of IPs per subnetwork is going to reduce. In the original network, we had 256 available IPs, but because we've borrowed one bit, we've now only got 7 bits left. Okay, so those 7 bits, 2 to the power of 7, is 128. the number of IP addresses per subnetwork is using the same formula, 2 to the power of n, but this time n represents the total number of bits remaining. And we've got 7 bits remaining out of the 8 bits. So 2 to the power of 7 is 128. Therefore, we have got 2 networks because we borrowed just the 1 bit. 2 to the power of 1 is 2. But each of those 2 networks can only have up to 128 available IP addresses. So by borrowing bits from the host portion, you can create these subnetworks within your main network. Now, one of the other things that you need to be aware of over here, so we have just extended our network. We've basically created 2 subnetworks by borrowing 1 bit. Okay, so our corporate office, which was 192.168.10/24, okay, still exists. But by borrowing 1 bit, what we have done is we are effectively using 25 bits now. So we started off with 24 bits for the corporate network, but we extended it by 1 by borrowing 1 more bit, effectively making it 25 bits for the subnetwork, which is why you will see that the office staff network is 192.168.10/25 or 255.255.255.128. And if you look at the server room, you'll see that it actually is 192.168.128/25. Okay, and that is because the second network starts at 128. Remember, we've got only 128 IP addresses per network, and that's 0 to 127. Okay, because it starts at 0, and therefore to get to 128, you only need to go up to 127. So this network is going to have 1.0 all the way up to 1.127, but the server room network starts at 128/25, and that goes all the way up to 255/25. Okay, so by creating these subnetworks, bear in mind also how the individual networks will work, because they are a subset of the main corporate network. Okay, the main corporate network was 192.168.10 all the way up to 192.168.1.255. But now we've got these 2 subnetworks, so we extend the CIDR notation. Now this is going to be a /25 rather than a /24. And furthermore, because we have 2 networks, 2 subnetworks within the main network, they also start at different ranges. So this one starts at 192.168.10/25. But this one, the server room, will start at 192.168.1.128/25. Okay, so hopefully this is starting to make a lot of sense. Just to make things slightly more complicated, okay, there's something else you need to understand about networking, especially when you create networks and subnetworks. Each network has certain IP addresses that are reserved. The first IP address on every network is what's known as the network ID, and the last IP address of every network is called the broadcast ID. So I've been going on about the fact that if you have a class C network with a /24, that's 255.255.255, that will give you the last octet for IP addresses available for your host machine. Because there are 8 bits, it's 2 to the power of 8, which is 256 available IP addresses. 0 to 255 is going to be the range. However, in real world, that's not the case, because the first IP address of every network is also known as the network ID. You cannot use that. And the last IP address of every network is the broadcast ID. You cannot use that either. So the number of usable IP address per subnetwork needs to follow a different formula. 2 to the power of n minus 2, where n represents the total number of bits remaining. So in real terms, even though we were going on about the fact that each network would have 128 IP addresses, actually that's not the case. It's going to be 128 minus 2, which is 126. And so if we take a look at the number of networks created, we've got 2 subnetworks. Subnetwork 1, which is the office staff network, has a starting IP of 192.168.1.0. That's the network ID. And it ends in 192.168.1.127, which is the broadcast ID for that network. What remains in between are the number of usable IP addresses. For subnetwork 2, which is the server room network in this example, the starting IP range is going to be 192.168.1.128, and the broadcast ID is going to be 192.168.1.255. What remains in between is the number of usable IP addresses for the server room network. And so hopefully this makes a lot more sense now in terms of how your networks are built. Okay, so let's do a quick quiz. You're going to create subnetworks within the range of 192.168.1.0/27. You want to borrow 3 bits from the host portion of your IP range to define your network. If you're borrowing 3 bits, if you're doing a /27, it also means that you are going to turn these 3 bits to ones. So 2 to the power of 7 plus 2 to the power of 6 plus 2 to the power of 5 is going to give you a subnet mask of 224. What does that actually mean? Well, let's work out the number of hosts that you're going to have. You have 1, 2, 3, 4, 5 bits left for the host portion of your subnetworks, okay? And so the number of hosts per network is going to be 32 minus 27, because you're using 27 bits for the network. That leaves you with 5 bits. 2 to the power of 5 is 32. So you have 32 available IP addresses per network. But remember the n-2 formula to get to your usable IP addresses. So 32 minus 2 is going to give you 30 hosts per network. How many networks are you going to have? That's the next question. That should be easy. You're borrowing 3 bits. So you're going to have 2 to the power of 3 or 8 networks in this configuration. And each of those 8 networks can host up to 30 usable host machines having usable IP addresses. And that's how you can quickly work out how many hosts you can have and how many networks you can have using CIDR notations. That brings us to the end of this video. I hope you found it really useful. I'll see you folks in the next. Thank you.